Hello and welcome to 8.2, Integration by Parts. So integration by parts is a technique that can be applied to a variety of functions, particularly useful in integrands, involving products of algebraic functions. So theorem 8.1, integration by parts, is how it's spelled out. If u and v are functions of x and have continuous derivatives, then, and that's important, they have to have continuous derivatives, then the integral of u dv, so you'd have identified one function to be u, the other function to be dv, the derivative of some function, is equal to uv minus the integral of v du. And guidelines for integration by parts: try letting dv be the most complicated portion of the integrand that fits a basic integration rule. That's important, basic integration rule. Then u will be the remaining factor or factors of the integrand. Try letting u be the portion of the integrand whose derivative is a function simpler than u, something easier to work with, because you're going to have du in this part. Then dv will be the remaining factor or factors of the integrand. Okay, look at example 1 here. Identify u and dv for finding the integral using the integration by parts. Do not evaluate the integral though. Okay, and I need to move that cursor because it's kind of right over what we're working on. We have the integral of x squared e to the 2x. So in this case, the more complicated one is e to the 2x. So you might say your dv is e to the 2x, and the u would then be the x squared. Oh, I forgot, e to the 2x dx. Don't forget those dx's. For example 2, find the integral. So we have the integral of 2x over e to the x dx. So think of this as integral of 2x times 1 over e to the x dx. That's a 2, not a d. It looks like a d. X, okay. So in this, we can say, if we say u equals the x, du equals dx, that means that 1 over e to the x dx, that's our dv, so v must be negative e to the negative x. So if you were to integrate that, you'd have negative e to the negative x. So we have the integral of u dv equals uv minus the integral of v du. So we have, again, integral of 2 times x times 1 over e to the x dx. That's 2 times the integral x e to the negative x dx. That's 2 times the integral of u dv. That's going to be 2 times uv minus the integral of v du. So I'm doing the substitution here, where my u was the x, this part was my dv. That's u. Here's our dv. So to integrate this, now that I can set it up in that format, it's going to be 2 times, because this 2 is out front, uv, u times v, minus the integral of v du. So our u is x. So x times, forgot my 2. 2 times x times, our v is negative e to the negative x, minus the integral, and let's put a parenthesis here, of v du. That's negative e to the negative x, and our du is dx. So, sorry, we're getting a little low here. That's going to be 2 times the quantity, negative x e to the negative x, minus negative is plus the integral of e to the negative x dx. That's going to be 2 times the quantity, negative x e to the negative x, plus, and this antiderivative is going to be negative e to the negative x. plus c, call that c1. So we have negative 2x e to the negative x here, minus 2 e to the negative x plus 2c1. We'll just call this, let's call that c. So it's negative 2x e to the negative x minus 2 e to the negative x plus c. That's it. Feel free to pause that one. If you need some more time, I'm going to scroll on and erase. Okay, here we have, for example 3, integral of x e to the 2x over 2x plus 1 squared dx. So if we identify this, well, think of this as integral of x e to the 2x times 1 over 2x plus 1 squared dx. So if we identify that our dv is going to be 1 over 2x plus 1 squared dx, excuse me, v is going to be the integral of 1 over 2x plus 1 squared dx. And that's going to be negative 2x plus 1 to the negative 1 times 1/2 plus c. So that our v is negative 1 over 2 times the quantity 2x plus 1 plus c. Our u then would have to be x e to the 2x, so that du would end up being, the derivative of x is 1, so 1 times e to the 2x plus x times 2e to the 2x, because the derivative of e to the 2x is e to the 2x, and the derivative of 2x is 2. Dx, so what we're going to have here is e to the 2x times 1 plus 2x dx. Or you can say e to the 2x times 2x plus 1 dx. And this looks a little familiar right there. So our integral of x e to the 2x over 2x plus 1 squared dx is going to be, this is our u dv, it's going to be uv, and our u we said was x e to the 2x. Our v we said was negative 1, so times negative 1 over 2 times 2x plus 1 minus the integral of, v du. So here we're going to have our v du. V we said was negative 1 over 2 times 2x plus 1 times, and then we have our du, which worked out to be e to the 2x times 2x plus 1 dx. Now the nice thing here is that we can divide stuff out. In fact, I'm going to kind of write with a different color. I wish I had my red pen, but I left it in my office, I think. So here's u, here is v, then here we have the integral, u times v, minus the integral of v, that's right there, and then this part is my du. Now this will simplify a little bit. Watch this. Ready for this? Kind of cool. E to the 2x plus 1 will divide by the 2x plus 1 down below. So now we have, it's a little nicer, x e to the 2x, I should say negative, over 4x plus 2 plus integral of e to the 2x over 2 dx. And you could have pulled the 2 out if you wanted, which will give us a final result. This integral is not so hard to do. Negative x e to the 2x over 4x plus 2 plus, so the antiderivative for e to the 2x is going to be e to the 2x over 2. So it's x e to the 2x over 4x plus 2 plus e to the 2x over 4 plus c. Okay. A little bit of a long process. You start working through it, you're going to start seeing patterns, start seeing ways to break it down. You might actually choose the wrong u and the wrong v in the first case, or dv, to try again. You know, I know it uses paper, but okay. Let's look at example 4. We have x cosine x. So the simplest part of this, if you said u equals x, your du is just dx. It's not so bad. And if you said your dv was cosine x dx, your v would have to be the antiderivative of cosine, which is going to be sine x. So the integral of x cosine x dx, which is like saying the integral of u dv, is equal to our u, which is x, v, which is sine x, minus the integral of v, which is sine x, du, which is dx. Hey, that's not a bad one to do at all. Integral sine x dx. So minus the integral of v du. I smashed my pen. Okay. That's going to be x sine x minus, so the integral of sine x dx is negative cosine x plus c. So it's x sine x plus cosine x plus c. So feel free to pause. I have to walk over here and scroll this up. It's a good time to pause if you need some more time. So I'm going to scroll and erase. So now we'll look at examples 5 and 6. Okay, we have the integral of e to the 2x sine x dx. I know last time we made the sine x, or the trig function, the dv, but this time we're going to go the other way with it. I'm going to say u equals sine x. So du is going to be cosine x dx. Our dv then would be e to the 2x dx, and v is going to be 1/2 e to the 2x plus c. And we don't really need the plus c's on this. We'll save that for the very end of the problem. Okay. So this is actually going to be a two-parter. This is part 1. We'll redefine for part 2. You'll see what happens. We have our integral of e to the 2x sine x dx, u dv, equals uv, so sine x times 1/2 e to the 2x, minus the integral of v, which is 1/2 e to the 2x du, which is cosine x dx. Okay, so this part's worked out, but oh, this led to another trig function. Okay, we can do this though. So let's focus on this part right here. The last integral. Because that's not an obvious integration. That's not going to be something we can just come up with easily. So if we can examine the integral, and we'll come back to this. Examine the integral of 1/2 e to the 2x cosine x dx. And in this case, we say u equals cosine x. So that du is negative sine x dx. Our dv would be 1/2 e to the 2x dx. And v would be, this integration would be 1/4 e to the 2x. We could have pulled this 1/2 out. It's fine the way it is though. So that when we have the integral of 1/2 e to the 2x cosine x dx, we have our u dv equals u, which is cosine x, v, which is 1/4 e to the 2x, minus the integral of v, which is 1/4 e to the 2x, du, which was negative sine x dx. So if I put this part here in place of this here, let's see what happens. So let me start off, we'll put what we had here. Integral of e to the 2x sine x dx equals 1/2 e to the 2x sine x minus, putting all this in here now. So I'm just going to be doing minus of all this stuff. So we'll worry about the negatives now, because I'm not getting low on space. So cosine x, I'm going to write like this. 1/4 e to the 2x cosine x. We have minus the negative of a negative, carries it through as a minus. 1/4 the integral of e to the 2x sine x dx. So what's really cool about this is you might start seeing something looks familiar. We started with this, and so at first you may see this and say, oh no, this can't be solved. This is it. We're stuck. We're going to be stuck in this loop forever and ever. And I'll be doing this problem until my final days. But no, that's not what's happened. That's not what we're going to do. You could keep doing that. Or you could say, well, this is here. This integral is here. Integral's over here. What if, make sure I had the coefficients all correct, I added 1/4 integral e to the 2x sine x dx to both sides. And we'd have 5/4 the integral of e to the 2x sine x dx equals this expression, 1/2 e to the 2x sine x minus 1/4 e to the 2x cosine x. Well, look at that, and I'll probably should say a plus c1. So to solve this, multiply both sides by 4/5. So that our integral of e to the 2x sine x dx is equal to 4/5 times 1/2 is going to be, what, 2/5 e to the 2x sine x. 4/5, doing the reciprocal here, times 1/4 is going to be 1/5, so minus 1/5 e to the 2x cosine x plus, and then 4/5 times c1, we'll just call that c. And there's our result. So we had to do it once, and then a second time, and the second time gave us an integral that was the same as what we started with, so we can subtract that, or in this case add that to both sides, and have the integral on one side, another expression on the other side, and get rid of that coefficient. Okay. You could factor some stuff out, but I'm going to leave it like that. Okay, next one. Solve the differential equation y prime equals natural log of x. So this is saying dy dx equals natural log of x, so that the integral dy equals integral natural log of x dx. So y equals the integral of natural log of x dx. Probably thinking, well, I don't have a lot of choices for my u and my v. I have a function, I have a dx. So in this case, my u is going to have to be natural log of x, which means du is 1 over x dx. My dv is going to have to be dx, which means v equals x. So y will equal the integral of natural log of x dx. That's going to be equal to, so this is my uv equals udv equals uv, so natural log of x times x minus the integral of v du. du is 1 over x dx. So y is going to be equal to x natural log of x minus integral dx. So y equals x natural log of x minus x plus c. Okay, feel free to pause on either of those. Well, because you can pause. At this point, you probably paused on 6. We're going to go on to the next page, the last page of this section. So now we have a summary. Oh, that looks really garbled with all the other writing on there. For integrals of the form x to the n e to the ax, x to the n sine ax, and a could just be 1, and x to the n cosine ax, dx in all those cases, let u be x to the n, and then our dv would be e to the ax dx, or sine ax dx, or cosine ax dx, and you go from there. For our integrals of the form x to the n natural log of x dx, x to the n arcsine ax dx, or x to the n arctangent ax dx, u is going to be the natural log, the arcsine, or the arctangent, and your dv is going to be x to the n dx. For integrals of the form e to the ax sine bx dx, or e to the ax sine bx dx, or e to the a, there should be an x. I think there's a typo there. E to the ax cosine bx dx. U is going to either be the sine bx or cosine bx, and dv is going to be e to the ax dx. E to the ax dx. Okay. There's another way of doing integration by parts. This is kind of a shortcut way to do it. And it works in most cases. Sometimes it's just not convenient to try this approach, like when it's going to loop around especially. So in the tabular format, you're going to choose u to be the term, the factor that will, if you keep taking the derivative, it'll go away. Your dv is the other part. So in this case, if I keep taking the derivative of x to the cube, I'll eventually get to a 0. So that's where I'm going to choose that to be my u. U equals x cubed, and therefore my dv is going to be e to the negative 2x dx. So u and v, or dv. So u is x cubed, dv is e to the negative 2x dx. So for this column, we're going to take the derivative. for this column, we're going to do the antiderivative. So let's go forward. So the derivative of x cubed is 3x squared. Derivative of 3x squared is 6x. Derivative of 6x is 6. Derivative of 6 is 0. We're done there. Now we're going to take the antiderivative for as long as we have a term over in this left column. So the antiderivative here would be negative 1/2 e to the negative 2x. Antiderivative is going to be positive 1/4 e to the negative 2x. Antiderivative is negative 1/8 e to the negative 2x. Antiderivative is 1/16 e to the negative 2x. So I'm dividing by negative 2 in every instance. So this is the way it works. Your result is going to be this one times that, this one times that, this one times that, this one times that. So it's our integral of x cubed e to the negative 2x dx is x cubed times negative 1/2 e to the negative 2x plus 3x squared times 1/4 e to the negative 2x plus 6x times negative 1/8 e to the negative 2x. And then plus 6 times 1/16 e to the negative 2x plus c. So the result is negative 1/2 x cubed e to the negative 2x plus 3/4 x squared e to the negative 2x minus, and 6 over 8, that reduces to be 3/4 x e to the negative 2x. And then plus 6/16 is going to be 3/8 e to the negative 2x plus c. Okay, yeah, that's kind of fun. I feel like I'm missing a negative somewhere. This and that. Oh, I did forget something. It's plus, minus, plus, minus, plus. So that one's positive, this one we make negative. And this one is positive, positive, negative times positive is positive. This one is the negative. And then, yeah, so it was plus, minus, plus, minus. That looks right now, okay. So this gets a positive, this gets a negative, and that's why this comes out negative. This would have been a positive in there, and the negative times a positive is a negative. This gets a negative. Okay. Our last example from this section says find or evaluate the integral using substitution first, then using integration by parts. So for substitution, we could say u equals x squared. Why x squared? Because that's what's inside the cosine. So our du is going to be 2x dx. And we can get that out of here. So this could be written as 2x times x squared cosine x squared dx. So the 2x dx, that's our part of our du. And this is u, and this is u. Now the problem with this, I've used u, so I couldn't use uv when we go to the next step. We have the integral of u cosine u du. That's what we have. And following by integration by parts, we'll have our, I'm going to call it wv W will be U, dW will be du, and dV will be cosine U, du, and V will be sine U. So this will become, it'll be WV, so that's going to be U sine U minus the integral of V dW, sine U du. And that'll be U sine U minus, if we integrate that, we all know what that's going to be, negative cosine U plus C. So it's going to be U sine U plus cosine U plus C. And what was U? U was x squared. So it's x squared sine x squared plus cosine x squared plus C. That's it for 8.2. Okay. Let me know if you have any questions. Thank you.